was not recognized at all as being anything interesting when it was discovered. It was just a corroded lump about the size of a large dick. Anything from ancient Greece simply shouldn't have gear wheels. These were precision gears, with teeth about 1 millimeter long.
Around 60 BCE, a ship was sailing through the Straits between Crete and the Peloponnese. It passed the island of Egila, which had been known as a pirate hotspot just a few years earlier. Caught in a storm and unable to find shelter, the ship sank, taking the lives of at least 4 people. The vessel was likely a large merchant ship about 40 meters long, carrying amphorae filled with wine and other goods, antique marble sculptures, bronze statues, glassware, and a small mechanical object made of wood and metal. This curious device, about the size and shape of a shoebox, would have appeared to most as just a box of dials and gears. However, it was an analog computer capable of calculating cosmic cycles. This is the story of the Antikythera mechanism. The shipwreck's remains were discovered in 1900 by sponge divers from Simi while working off the coast of Antikythera, known in the ancient world as Egila. One of the divers, Elias Lecopantes, dove to a depth of around 40 meters. When he resurfaced, he was shaking, claiming to have seen dead naked bodies lying on the seafloor. Captain Demetrius Kontos decided to investigate and found that the bodies were actually marble and bronze statues scattered across the ocean floor, along with numerous other artifacts. To prove what he had seen, Kontos brought up a life-sized bronze arm for the rest of the crew to see. Realizing the significance of their discovery, the divers began collaborating with the Greek government and archaeologist Georgios Oikonomos to investigate the site. This became the first underwater archaeological excavation in history, and their findings were extraordinary. Alongside impressive bronze sculptures, divers recovered amphorae from Rhodes in Asia Minor, Parian marble statues from the Aegean, glass artifacts from Syria, Palestine, or Egypt, and coins made of silver and bronze from Ephesus and Sicily. The coins were minted between 76 and 67 BCE, suggesting that the shipwreck likely occurred sometime within the following decade or two. The variety of artifacts on board indicated that the ship may have been a merchant vessel heading to Rome, though some scholars speculate it was carrying looted treasures. The divers brought up nearly 100 marble statues and bronze sculptures, including the famous Antikythera youth, which dates back to the 4th century BCE. These statues captured the public's attention and were celebrated as the most exciting discoveries. Over time, the findings became less impressive, but in the following year, a telegram reported the discovery of a slab with an inscription that could not be copied. At the time, no one realized this corroded piece of metal and wood would later be identified as the world's oldest analog computer. The slab was nearly discarded before reaching Athens, as the focus remained on larger, more visually striking artifacts. Unfortunately, because it was not treated for preservation after removal from the water, it suffered some damage due to exposure. The significance of the so-called Antikythera mechanism didn't remain hidden for long. In May 1902, the corroded object split into 2 pieces. Accounts of how this occurred vary, but visiting archaeologist Valerios Stais noticed a metal gear emerging from one of the sections, as well as inscriptions written in Greek. This discovery triggered over a century of research, revealing the true importance of the artifact. The initial cleaning and preservation of the Antikythera mechanism separated the slab into 3 pieces, and today it consists of over 82 fragments. 4 fragments contain multiple gears, while many others include ancient Greek inscriptions. To give you an idea of the scale and extraordinary precision of this mechanism, the largest gear measures only 13 centimeters in diameter and originally had 233 teeth. The level of craftsmanship here is hard to put into words. The first translations revealed the phrase, "ray of the sun," which led some researchers to believe it was an astronomical clock. This discovery shocked other scholars, who argued that such advanced technology couldn't exist until the 14th century, suggesting the device must have belonged to a much later ship. Over time, more details came to light. The Greek word for one of the ancient Egyptian months was identified, hinting at a solar calendar, while the Greek word for Venus, Aphrodite, suggested a connection to lunar movements. By the 1930s, researchers proposed that the mechanism could have been an astrolabe or a planetarium showing the sun, the moon, and the 5 planets known to the ancient Greeks. Research stalled until after World War II, when British physicist and science historian Derek de Solla Price took a deep interest in the device. Price noticed that much of the original mechanism was corroded into the fragments and suggested that it was used to calculate time cycles and astronomical events. He believed it wasn't made for seafaring, but had simply been on a ship during its transfer to the intended owner. Price's persistence led to an important breakthrough in 1971, when nuclear physicist Charalambos Karakalos X-rayed the fragments, identifying 30 gears. Price attempted to reconstruct the mechanism based on the X-rays, but his version was complex and didn't match the delicacy of the gear teeth. It was still an impressive attempt, considering the challenge. In the late 1980s and early 1990s, researchers Michael T. Wright and Al Bromley revisited the device with linear tomography to gain new insights. The most advanced studies began in 2005 with the Antikythera Mechanism Research Project, in collaboration with the National Archaeological Museum. Researchers used CT scanning and polynomial texture mapping, now referred to as reflectance transformation imaging (RTI), to enhance the visibility of surface details. The CT scans were instrumental in revealing the internal mechanical structure of the fragments and even uncovered hidden inscriptions. These techniques also made visible inscriptions on the gears and other metal pieces much clearer. So far, about 3,000 of the estimated 15,000 characters have been transcribed. Researchers believe they have recovered approximately 30% of the original mechanism. All of the work and further research from this imaging has significantly improved our understanding of what this mechanism was used for and how it functioned. So, let's get into it. The Antikythera mechanism essentially acted as an analog astrological computer. If you're unfamiliar with an analog computer, think of a non-digital wristwatch as a basic comparison. The mechanism was a box measuring approximately 30 centimeters high, 20 centimeters wide, and 10 centimeters deep. It featured rectangular bronze plates on the front and back faces and was enclosed in a wooden casing. A knob on one side controlled the internal gears. The front face displayed a circular dial surrounded by 2 concentric rings with different scales of measurement. The inner ring was fixed and divided into 12 sections, each marked with a zodiac symbol. Each section contained 30 evenly spaced ticks, reflecting Babylonian astronomy, where 1/12 of the ecliptic, the sun's path around the earth over a year, was equally assigned to each zodiac sign. This design allowed the mechanism to predict eclipses using the ancient Babylonians' Saros cycle, which spans 223 lunar months, or just over 18 years. The second ring was removable and rotatable, marked with the months and days of the Egyptian calendar written in the Greek alphabet. This calendar had 12 months of 30 days, plus 5 additional days at the year's end. Since the Egyptians did not observe leap years, their calendar drifted through the zodiac over about 120 years. This is why the ring had to be adjustable, accounting for the shifting alignment of the calendar with the zodiac. The front dial also included multiple pointers extending from its center. One was a lunar pointer that displayed both the position and phase of the moon. A small, half-black, half-white ball attached to this pointer rotated alongside the dial, visually representing what the moon would have looked like. This mechanism accurately followed the moon's accelerating and decelerating elliptical orbit using epicyclic gearing, the first known instance of its kind. Additionally, the dial included a solar pointer, which showed the sun's position on the ecliptic and possibly the day of the year. It also depicted the orbits of the 5 planets known to the ancient Greeks at the time: Mercury, Venus, Mars, Jupiter, and Saturn. The back side of the mechanism had 5 dials, 2 large spiral slots inscribed with scales and radial dials, and 3 smaller circular dials with small pointers. The top spiral is known as the Metonic dial, divided into 235 sections. Each section represents a lunar month and includes the Corinthian names for the months. This aligns closely with the 19-year Metonic cycle, where the lunar phases repeat at the same time of the year. The Calippic cycle, which spans 76 years, was also part of the system. This cycle is essentially a longer version of the Metonic cycle and helped convert lunar and solar years within the mechanism. The bottom spiral was similar but simpler, used to predict the time and day of eclipses, in addition to the month. Whoever operated the mechanism had to carefully reset the pointers by lifting the pin and repositioning it at the start of the spiral once the pointers reached the end. The game's dial is another key feature on the back. It's the only pointer that moves counterclockwise and was used to calculate the timing of the Pan-Hellenic Games, including the Olympics, Isthmian Games, Nemean Games, and Pythian Games. It also calculated the dates for two smaller events, the Games of Na and the Games of Aleia of Rhodes. Around these dials, tiny Greek inscriptions were delicately carved into the bronze, filling available free space. Additional text was inscribed on the front and back bronze plates, which served as covers. Parts of over 50 lines on the back cover inscription remain readable, providing a systematic description of the external dials, similar to a user manual. The current reconstruction of the Antikythera mechanism includes 69 gears working together to move the dials, though some experts believe there may have been even more components originally. The Antikythera mechanism was an astronomical calculating machine that allowed users to set a date via its calendars and observe the positions of planets, the moon's orbit and phases, and the eclipse cycle. Initially, when the mechanism was discovered on a ship, it was thought to be a navigational tool. Another theory suggests it was created for demonstrative or educational purposes, rather than for professional astronomers, who would have required a much more precise device to measure fractions of days and the varying lengths of days and nights. Instead, the mechanism was likely used to teach philosophy students and members of the elite about the stars, planets, and their influence on Earth and society. Given its small size, it was probably designed for individual lessons or small tutorials, rather than as a prop for large group instruction. Its level of sophistication also suggests it was intended for specialized learning rather than standard education. The Antikythera mechanism highlights the advanced craftsmanship of the ancient world. Although ancient Greeks were known to use gears, this device demonstrated an unexpected level of detail and precision. Its gears, carefully cut from bronze sheets, were optimized to reduce friction. What makes the mechanism particularly significant is that it survived when most ancient bronze and copper artifacts were recycled. It is highly likely that other devices like the Antikythera mechanism existed, including precursors and possibly even more advanced versions. However, because metal was a valuable resource, many similar artifacts would have been melted down and repurposed. The Antikythera mechanism itself may have been made using recycled metal from an earlier device. Cicero, writing in the 1st century BCE, described two machines created by Archimedes in the 3rd century BCE and one by the philosopher Posidonius in the 1st century BCE. These were referred to as celestial globes, capable of reproducing astronomical motions such as eclipses and planetary movements. The ancient Greeks and Romans clearly understood the variable speeds of the moon's orbit and predictive gear technology. However, until the discovery of the Antikythera mechanism, there was no physical evidence of what such a device would look like. It confirms that machines of this kind, though rare, were known and likely produced more than once in history. Nevertheless, creating these mechanisms would have required thousands of hours of labor and significant cost, which means they were not items of mass production. Archimedes likely laid the groundwork for the creation of analog celestial computers like the Antikythera mechanism. This device was made sometime after Archimedes' death in 212 BCE during the Battle of Syracuse, suggesting it was created by a student or follower who understood his calculations. The astronomer or scientist responsible for the mechanism probably didn't work alone, as crafting something with this level of precision required collaboration with bronze smiths and other master craftspeople. A project of this scale was clearly a team effort. Initial measurements and the inscription referencing the Corinthian month led to the belief that the Antikythera mechanism was created for someone in the Corinthian colony of Syracuse. However, further analysis suggests its origin might point to Epirus in northwest Greece. This location aligns with the ship's possible route to Rome, particularly because one of the dials references the Pan-Hellenic Games. Interestingly, one of these games took place in Rhodes, located far from Epirus. This has led to another theory, as some rulers of Epirus had ties to Rhodes, and the astronomer Hipparchus, who lived in the mid-2nd century BCE, was based there. The mechanism incorporates Hipparchus's theory about the moon's motion, strengthening this connection. Ultimately, as with much of archaeology, we may never be certain of its exact origins unless a clear marking is found on the device. It's also possible that the mechanism was simply en route to Rome, where Greek artifacts were highly valued. At the time, wealthy Romans often sought out impressive pieces like this to display in their homes. The creation date of the Antikythera mechanism has been a topic of debate for years. Since it functioned as a collection of calendars, it required a calibration date to ensure the planets moved around the dial accurately. Some scholars have pointed to eclipses that occurred around 204 BCE as a reference point. However, in 2022, others suggested that the initial calibration date was December 23rd, 178 BCE. It's important to note that these are calibration dates, not construction dates, but they provide a useful window into when it may have been created. This means it could have been built slightly earlier to predict celestial events, or a bit later, using recorded eclipses for calibration. The existence of the Antikythera mechanism shows that the ancient Greeks had a much more advanced understanding of astronomy than we previously thought. Their knowledge rivaled scientific achievements from the 16th century. Even experts who have spent their careers studying the device have admitted that its level of technology is hard to believe for that time period. Yet, it undeniably dates back to the Hellenistic age. The Greeks came remarkably close to inventing clockwork hundreds of years before it was formally developed. Unfortunately, due to the lack of widespread documentation or further replication of the Antikythera mechanism, its potential wasn't fully realized. If this technology had caught on, it might have pushed the Enlightenment and the Industrial Revolution forward by millennia. Arthur C. Clarke, the author of 2001, A Space Odyssey, once remarked that if the Greeks' insight had matched their ingenuity, humanity might not just be exploring the moon, we could have already reached nearby stars. While we haven't traveled to other star systems, the Greeks and Romans succeeded in bringing the stars closer to Earth. The legacy of the Antikythera mechanism extends beyond its technical marvel. It represents a deep curiosity about the cosmos, a desire to understand celestial events and their connections to human life. The ancient Greeks were not only interested in practical applications like navigation, but also in the philosophical and religious significance of the heavens. The stars, planets, and lunar cycles were often viewed through the lens of mythology, influencing cultural practices and even the structure of society. The mechanism, with its precise calculations, could have served as both a teaching tool and a symbol of this profound connection between science and spirituality. While the Antikythera mechanism was a product of Hellenistic Greece, it is clear that this kind of scientific inquiry and technological development was not an isolated phenomenon. The Greeks were part of a broader Mediterranean world where ideas and inventions traveled and evolved. The mechanism's complexity suggests that there were ongoing advancements in mathematical and astronomical thinking, possibly influenced by earlier civilizations such as the Babylonians, Egyptians, and Mesopotamians. These cultures, with their own sophisticated systems for tracking celestial events, might have provided the foundation for Greek innovations. The melding of these traditions in the Antikythera mechanism reflects the interconnectedness of ancient intellectual history. The rediscovery of the Antikythera mechanism in the early 20th century opened a window into a forgotten era of ancient engineering and knowledge. However, its true significance only began to unfold as modern technology allowed for the detailed analysis of the corroded remains. X-ray imaging and other advanced techniques revealed the intricate workings of the device, shedding light on its complexity and refining our understanding of ancient technology. These discoveries have sparked a renewed interest in ancient scientific achievements, reminding us of the remarkable intellectual capacity of ancient civilizations. In many ways, the Antikythera mechanism is an early precursor to the kind of technological advancements we associate with the modern era. Its design embodies the idea of a machine that can predict future events with accuracy, a concept that would become central to later developments in computing and mechanical devices. The ancient Greeks, through their work on devices like the Antikythera mechanism, laid the groundwork for centuries of scientific progress. What they achieved, despite the limitations of their time, continues to inspire modern scientists, engineers, and historians. Thank you for watching. If you enjoyed this video, don't forget to hit the like button and subscribe to the channel.